All right, so for today's class, we're going to look at visual sensation. Vision is the sensation we trust the most, and so this is going to be a big unit where we're going to talk about vision for 2 days. Today, we're just going to look at the sensation side, so how do we take in light sensory imagery and able to process that and understand it. Again, just like I did with hearing, I've altered the notes to focus just on the things that are most likely to show up on the free responses. But the full notes are all posted on the on the GC website. So if you're interested in learning more about the eye, you can go review those notes, or it'll be talked about more in depth in the study guide pages that correspond with today's worksheet. All right, in order to hear, you need air, which means in order to see, you need light. If you're put in a completely lightless room, you'll be blind. You won't be able to see or perceive anything. Right? But we aren't ever really in a completely lightless room. We might be in very dark rooms, but there's usually some light energy that's maybe seeping under the cracks in the door or light that's filtering through the blinds. And so our eyes adjust, but it's more just our eyes being able to make use of the light that's present within the environment. So you need to light in order to be able to see anything. Just like with hearing, there are certain frequencies that are outside the human threshold that we can't hear. There are certain light waves that are outside of human thresholds that we just can't see. And so for us, our visual spectrum is those rainbow colors that you see here between 700 nanometers and 400 nanometers. And so that's the only visible light that we're capable of seeing and interacting with. Right? How this works is light energy is constantly bouncing off of everything around us. How we perceive the color is what is the light wave that bounces back off the object and then into our eye. And so it's only the certain light waves that correspond with the color of the fabric that we're wearing or the paint that's on the wall that actually will reflect back that one narrow bandwidth of the light waves. There's a really good Magic School Bus episode that talks about this and how color vision works. So if you're bored, I think Magic School Bus is on Netflix, so you can watch the light energy episode, and it kind of puts it into an easier to understand element, this light reflection description that I just try to do. All right, for light energy, for us to be able to detect the color, that's what we need the wavelength for. Right? That's where we can see the hue of what the color is going to be. The slower wavelengths will come across our visual spectrum as being more of a red color, and then the faster wavelengths will come across our color spectrum as being a purplish color, a violet color. And so we use the wavelength to let us know the hue and what exact color am I looking at. The amplitude of the wave lets me know the intensity. All right, how bright or dark is that color? So the higher the amplitude, the brighter that red, the brighter that violet. But the lower the amplitude, the less intense that color comes across. And so it might be a darker or more faded, dim red or purple that we're looking at. So we still use wavelengths, but it's the light energy wavelength that we're measuring in order to depict the hue, the color that we're seeing, and then how much of that light energy is there, how high is the amplitude of that wave for us to get the brightness and the vibrancy of that color. Oops. All right, so we're not going to go over all of the parts of the eye. We're just going to talk about two in particular. We're going to look at the lens. Right? The lens is the part of your eye that's responsible for focusing and sharpening that light energy so that you can see and focus on what you're seeing. So our visual acuity is built upon the lens. If you look at the picture down at the bottom, the lens is that hard glass object that you see in your eye right behind the pupil. I know when I was at Good Counsel, the biology classes, we would dissect eyes sometimes. You could actually find the lens. It was a hard pellet just in the center of that eye. The goal of the lens is to properly focus the light onto the retina. Right? The retina is the back of your eyeball, and it's covered in all of your sensory optic nerves so that you can be able to receive that light and then start transmitting it into some neural processes for our brain to make sense of. And so our retina is covered with all of these sensory cells that will receive and understand that light. If the lens doesn't properly focus the light on the retina, you won't be able to see things properly. So for example, if you take your hand out and place it like arm's length away, you can focus and stare at your hand, but the wall behind your hand is going to look a little fuzzy, a little blurry. Versus if you change your focus and now focus on the wall behind you, well, now all your hand looks a little blurry. Maybe you see fictional, like 6 or 7 fingers now attached to your hand. Right? That's because of what your lens is doing and how it's focusing the light so that your retina can easily see what you're looking at. Right? The most important part of the retina is the fovea, and you can see that depicted on the picture at the bottom with the upside down candle. Part of what the lens does when it focuses the light is sometimes the image gets flipped on your retina. Your brain flips it right side up, so you never see the world upside down. But it is kind of how the images are all depicted. And so our fovea is our center focus part, and the most sensory nerves are located there within the fovea. All right, but let's talk about the lens a little bit more before we move on to the retina and the fovea and why those are important. Right. Again, your lens is responsible for visual acuity. And so having the lens perfectly crafted is how you're able to see clearly and crisply. But if there's an abnormality within the lens, if the lens isn't doing its job properly, that'll lead into visual problems. What LASIK surgery does is it uses lasers to try and cut and reshape the lens within your eye so it'll do its job properly so that you don't need glasses or contacts to see clearly. All right, individuals that are nearsighted, like for example, I'm nearsighted, that's why I have to wear contacts. All right, you can easily see things that are near to you, but things that are far away are blurry and difficult to see. Right, so nearsighted means I can see what's near. It calls out what you can easily see. And we think that nearsightedness might be part of a developmental process, and so your visual sensations are shaped by what you've experienced. We know that children who've slept in the dark are very unlikely to develop nearsightedness, but if you sleep in a lighted room, you're much more likely to develop that nearsighted visual problem. Right? And so maybe it's just the constant light that's filtering through even your closed eyelids. It's leading to an inability to easily see, and that's what's leading to these problems with vision. Versus farsightedness. With farsightedness, that's an inability to see things that are close to you, but you can easily see things that are far away. All right, what's happening with farsightedness is your lens is actually focusing the image behind where the retina is. Where with nearsightedness, the lens is focusing the image in front of where your retina is. All right, so individuals that are farsighted, this usually happens more often with older individuals than younger individuals. But for example, it would be if you are ever at a restaurant and your parents have to hold the menu away from them so they can see what's written there. It's because putting it further away actually makes it clearer and crisper on their eyes. And so with farsightedness, the lens is not doing its job properly in the sense where it's focusing the images behind where the eye is. And so you need the lens to work properly in order to easily see items. So here's a silly, simple vision test. If you look at this picture, most people will see Albert Einstein, but individuals that are nearsighted who aren't wearing their glasses, contacts in the moment, they're much more likely to see Marilyn Monroe. If you want to test this for yourself, put your iPad, your laptop at the end of the room and then walk backwards, and eventually the face will transform into Marilyn, and you can see the differences between the two. So if you want, take a minute or so. I'll leave this up for a second. All right, now let's talk about your retina. Your retina, we have all your sensory cells there. And so our sensory cells for vision would be your rods and your cones. All right, the rods are on the edges, the periphery of your retina. And they're really good for peripheral vision. They get activated very quickly. So being able to see something out of the corner of your eye relies on rod activation. It's able to get big picture items, so movement, things like that. It can tell the difference between black and white color, so something that's light and dark, but it's not good with color detection. In order to get color detection, you need activation of your cones. All right, your cones, they are in the center of your retina. They're basically the entirety of the fovea. All right, and your cones are good for finer details, more like feature detection type things. They're responsible for color vision, and so being able to detect what color you're looking at. Individuals who have night blindness. Night blindness is when it's in periods of twilight transitioning between day to night and night to day. Right? Your rods are activating, you can still see, but your cones aren't working properly, and so you can't get those fine details. For example, I have an uncle who is not allowed to get a driver's license because he has really, really bad night blindness, and so they just don't want him driving on the roads during these transition light periods because he wouldn't easily be able to detect the cars and the traffic patterns around him. And so your retina have these rods and cones to help them receive the sensory light image and try to transmit it into something that's usable for our brain. Right, so if you look in this picture here, you can see the rods. They look like rods, they're little gray sticks. And then you have the cones, which look like cones, those red, green, blue little cone-shaped things. Right? Most of the light is going to be centered around the fovea. So again, the fovea is all cones and no rods. All right, most of our optic nerve, most of our visual sensation is going to come from things that are placed within the fovea. And so our eyes are constantly moving around our environment to allow the light energy from all the different parts of the room to eventually have a chance to land on our fovea, so that information can be sent to our brain. And then our brain puts it all together into one continuous shot, one usable whole, so that you can understand what's happening. So in order for us to visually see something perfectly, that light energy needs to fall on the fovea, which is the very center focus part of the retina, and it's where we have most of our sensory nerves. All right, so with the fovea and with all the color vision, let's talk about how do we use all of this. All right, the cones are responsible for sending color light. The more cones that are activated, the more likely we are to see the different hues that are present. All right, we have cone receptors that are sensitive for red, for green, for blue. And so the more activated those three are, the more we're going to see the different light elements. All right, now I know art people, you're saying, well, green's not a primary color. Why is green on that list? I don't know, because biology doesn't follow art theory, I guess. But those are what the different parts of the eye are going through. If you have an issue with one or more of your cones, you could develop color blindness. Right, so we know that there's a lot of people in the world who are colorblind. It's much more common to be male than female because it's just something that's carried on that Y chromosome. And so it's dealing with color sensitivity. All right, the most common form of color blindness is red-green color blindness. And so you have an issue with maybe the red or the green sensitivity cone. There's also blue-yellow color blindness. It's a little bit rarer, but it's because you're having issues or problem with that blue cone. Very, very rarely, there are people that have complete color blindness, and so they see the world in shades of gray. But usually that's not just a cone problem, that's also something happening within your brain where there is a problem either within the thalamus or within the occipital lobe. All right, but to get good color vision, you need more and more of those cones being activated. And so it's this additive element of light theory. My stage crew in the theater department. If you ever play with like the lights and the gels, well, if you add more light to the field, that's what's going to get you the white color there. And so the same thing happens within your eyes. The more cones that are activated, the more colors and lights that you can see. And therefore, the more that are activated, the more likely you are to see something as a whitish color versus like a green or a yellow. All right, so with these colorblind individuals, it's usually a problem with those red-green sensitivity cones. So if you look at this picture here, it's a bunch of circles, but there's actually a number embedded in the center. Right? Someone who has red-green color blindness, sorry if you're someone who has red-green color blindness, you won't be able to see that the number 74 is right there in the center of this image. And it's because of that lack of activation of those cones that are there. Now, people with color blindness, it's not that they can't see the color, it's just that their color perception is a little altered. Right, so here's a picture that kind of illustrates that. Individuals with no color blindness, they'll be able to see the pencils under the regular slide. But people who have red-green color blindness, that's the center picture there. And again, that's the much more common form of color blindness. Or people who have blue-yellow color blindness, they'll see the image that's in the side on the right. And so again, it's not that they can't see color, it's just that their perceptions of colors are a little off and it doesn't align with what regular color vision is showing us. Right, now what also plays a role in your color vision is what's going on in your thalamus. Right, if you remember all the way back to the beginning of the year, your thalamus is the sensory switchboard where all incoming information comes through and your thalamus starts directing it to the upper level regions of the brain so you can make sense of all of this. All right, well, some of these neural cells, they're activated by certain color lights and then they're inhibited by that same opponent. In order to see green, we need to shut down red for a little bit. So what opponent process theory does is it tries to explain why do we sometimes have these after images flashing in front of our eyes. And they say it's usually something that's going on within your thalamus. As you stare at one color over and over and over again, you're actually overstimulating that cell. That in order to hopefully reset it so you can have a clear vision field for the next image you're going to look at, you'll have a brief after flash of the opposing color. And so opponent process theory states the reason why we see this after image, this flash of the different color, is because you've just oversaturated the cells that have been activated, and then those inhibited cells, when they get turned back on, well, now that they're going to flash a brief image because your thalamus gets a little confused by that thing now turning back on along the way. I know this sounds a little confusing, so let's practice this together. I'm going to put up an image, and I just want you to stare at the screen. Try not to blink. And then this will illustrate what's going on when your thalamus gets confused when that cell turns back on. All right, so just stare at the center of this image and try not to blink. Just a little bit longer. All right, how many people see a floating American flag in the center of this very blank white screen right now? If you blink, it'll slowly start to fade away. All right, so what you just saw, that's actually opponent process. By staring at that weird screen for so long, now this blank white field is going to give you an after image of the properly colored American flag that's present. So all of that's going on because of the cone activation and then how your thalamus communicates with those cones. So with color vision, our thalamus is also going to override some sensory information. We know that the world doesn't magically change colors all the time. If you look at this image over here, the A square is the exact same color as the B square. All right, this is similar to the opening of the Brain Games episode I gave you, where the top and the bottom squares of gray, they looked very different until you covered the center, and now you could see that they were all the same. All right, we know that the amplitude of the light wave lets us know how bright a color is, which means if I walk from the very bright sunny outdoors inside to a dark room, well, the intensity of the light bouncing off my shirt has changed, which means in theory, I actually have a differently colored shirt on now than when I was standing out in the sun. But that's not how the real world works, and so our brain knows this. And so it naturally adjusts images to keep the color constant, right? Things that are in the shade, like that B square that looks like it's in the shade of the big green pillar, our brain is going to naturally tell us that is lighter, and the things that are out in the bright light, like this A square, our brain is going to tell us that's naturally darker, just to try and keep things consistent. And so our brain is going to kind of ignore some of the sensory signals that are coming from our eye in order to help us understand the world and keep some sense of consistency. And so it's built off of our previous experiences about how the world works so that we won't get confused by that A, B square problem. If you don't believe me, print off this slide and you can cut those squares out, but I promise you those two squares are the exact same color. All right, what we also have within our visual centers is we have quick feature detections. Right, these are nerve cells that are built to pick up on specific features, shapes, objects, things like that, so we can quickly make sense of them. Right, a lot of feature detectors are evolved traits. We have feature detectors that'll help us detect movement very quickly and easily. Right, so for example, in hockey, right, the goalie has a really hard job because they have to keep track of that tiny little puck on a giant field of ice. And so their feature detectors kind of help them easily detect those fast-moving objects so they can quickly respond without maybe knowing what it is that they're seeing. Right, also, a lot of feature detectors are built towards seeing faces. Right, since we are naturally social creatures, right, we are built to see faces in almost everything. And so a lot of our feature detectors are there for looking for eyes or the shapes of faces and mouths. And so we're able to perceive an object as being a face so we can respond to it and know if that's a happy face or an angry face. And it allows us to kind of see these. So for example, let's test your feature detectors. I'm going to show you 3 quick images, and I just wanted you to tell me, what do you see here? All right, so in this picture, what do you see? All right, what about this picture? What do you see in this image? And then finally, what do you see in this picture here? All right, so that's just our vision sensation elements. We'll talk about perception next class. Remember all of this stuff because it'll be part of the vision free response you're going to be assigned next class. But otherwise, you're done for the day, so have a good one.